I'm not using contact slides. Okay, so I'm sorry if it makes your life a little harder. I don't think it should, but it could be, so sorry for that. And the second thing is, I think that you'll discover that the notes have a few typos. They will be corrected in time, but it's sort of, you can't expect to have such a long document without a few typos. That's the two things I wanted to apologize for. I do have one request. If I go a bit too fast, or if you don't understand, just ask me. Okay? The idea is for you to understand what I'm doing, because I more or less understand what I'm doing, so I'm not lecturing for myself. Okay, so after that we can start, I guess. Is that better?
You can turn the gain on.
Turn what?
There's a knob on the right.
Okay. Is that better? I feel ridiculous. Okay. So, what I want to talk about is basically statistical learning theory. And I want to define the problem that I want to address, which is rather simple. So, your starting position is, you start with a class of functions f. So f is just a class of functions. Okay? They're defined on a set. Okay? And you know that this set has a probability measure on it. But you don't know the probability measure. Okay, so you know it's a probability space. There's a probability measure, mu, on... Okay. So a probability measure over here. You don't know what it is. Now, you have a function which can be any function in the world, assuming that it's bounded, for example. And what you're trying to do is to find, in some sense, the best approximation of your unknown function within your given class of functions. Okay? So you have t, which is a target function. And the problem is, find the best approximation in a certain sense of t in the class of functions f. In other words, find the function which in some way describes best the properties of t. Now, when I say that, it's really ambiguous because I haven't defined two very important things. I haven't defined what sort of way would I like to measure the similarities. Okay, I say that you want to find the function which in some sense best describes t. I haven't told you how I measure things, when a function is close or not to t. That's one thing. The other thing I didn't tell you is what sort of data you have. Okay, how do you construct this approximation? Okay, so let's start with ways of measuring if two functions are similar. So the way to do that, there are a million possible ways. But one way of doing that is to measure, to define sort of distances between functions. And one distance I'm going to use relates to this probability measure. Okay? So I'm going to define a distance between two functions. So the norm of f minus g with respect to LP mu, that's just a notation, you shouldn't be worried about that, as simply the integral of the difference of f minus g to the power p d mu power 1 over p. Now, the one p we will be particularly interested is p equal 2. So I'm going to lose the p, write 2 here. Okay? So that's the usual Hilbertian way of measuring distances. Okay? Now, the reason what I'm doing is integrating the differences between two functions, and I have to take into account the given probability measure. Okay? And since this is a probability measure and this is essentially a problem in probability theory, I denote this, okay, and I'm going to use this notation from here on as the expectation of f minus g squared half with respect to the probability measure. So this tells you what do I mean when two functions are close. I say the two functions are close if this quantity is relatively small. Okay? So now, let me formulate the problem that I sort of mentioned before. So now this is your class of functions. Okay? Just very sketchy. This is your target. And you want to find a function which is almost the best. Almost the best in this sense. Okay? So, first of all, let's define the best function. What would be the best function? It would be the function that minimizes the distances between t and elements of the class. Okay? So you're looking for a function, I denote this function by pf of t, let's call it g. This is the class g. Okay? pg of t, and pg of t satisfies, okay, satisfies that for every other, if I pick any other function g, this distance would be always greater than this distance. Okay? So the distance, let's write the norm of t minus pg of t in L2 mu is always less or equal than t minus g in L2 mu for every g in d. Okay? So this is the function I'm shooting for. I want to find this function. Okay? It's very difficult to find this, so I'm willing to relax things a bit. I'm not looking for that function particularly, I'm looking for a function which is close to this one. So a function which doesn't satisfy that the distance is the best possible, but slightly worse than the best possible. Okay? So that's what I'm actually shooting for. Now what sort of information will I have? Well, the information that I have is a sample. Okay? Remember, this is a probability measure on this domain. So I can sample according to this probability measure, which is just a weird way of saying that I'm generating a random point here, and in a way which captures this probability measure. Okay? So the data we have So the data we have is a sample. And the sample is just a set. xi, t at xi. I between 1 and n. Okay? So in other words, what I have are a certain number of points here. Okay? The values of the target function on these points. And using that information, I want to construct a function which satisfies this, which is almost the optimum in this sense. Okay? That's what we're shooting for. Now, one way of doing this is to define a class of functions associated with a problem, okay, which is called the loss class. Now, the loss class will be defined according essentially to do different things. First of all, the target. Of course, it depends on the target in the class. And it will also depend on the way I chose to measure things. But it will have to reflect the way I measure distances. Because I want it in some ways to be compatible with this distance if I chose this distance, or another distance if I chose some other way of measuring. So I define the loss class, the loss class, which is associated with the target T and your class of functions. Let's call it G from now on, just as in the notes, as the following set of functions. It's just G minus T squared minus PGT minus T squared. G is in G. Okay. Now let's look at this and see what we're measuring. First of all, it's a class of functions, right? You give me any value of x, I can tell you what the value of this function. With one problem, I don't know this. I don't know how to compute the value of any function within that loss class at x because I don't know this function. But as soon as I knew that function, it's well defined. Okay? That's the first issue. The second issue is, look what happens when I integrate this with respect to this probability measure. Right? Remember, this one is the best approximation of t within that class with respect to this distance. Right? So when I take the expectation of this, what I get this is what I get. Now this is just the distance between t and pgt squared, right, because we have the square root here. So this is just the distance between t and pgt squared. And this is the distance between t and g squared. So for every g in your class, this measures, in some sense, how far g is from being optimal, right? It's the distance between g and t squared minus the optimal distance squared. Okay? So, in some sense, finding something which is close to 0 here, if I find some g which is close to 0 here, I'm done. Right? Because what I want is to find a function which is almost optimal. This is always greater or equal than 0 because this quantity is always smaller than this. Right? And I want to make this quantity as close to 0 as possible. When, of course, all the data I have is the sample. Okay? Now, that's in general the formulation of a learning problem. So, you have a given class of functions, an unknown probability measure, and an unknown target. You sample your data according to that probability measure. Okay? You get this set, and you want to construct a function which almost minimizes this. Okay? Without any a priori knowledge of the function or the probability measure. Okay? So let's see. Is that clear so far? Yeah.
I'm just trying to work out what you mean by 1 stroke g minus t squared.
Absolute value. You can do it.
Line above. The absolute value.
Yeah. This is okay. Look at it like that. I define, for every g, I define sort of a loss function associated with g in the following way. And I have to tell you what's its value for every x. So the value of the loss function associated with g at the point x is simply g at x minus t at x squared minus this at x minus this at x squared. L is a class of functions. It's defined for every x. And of course, the main problem I have, and it's very important from the algorithmic point of view, I can't compute this. Right? I can't compute PGT at x because I don't know what PGT is. Right? Yes?
So PGT is not necessarily NG either.
It is. It's the definition of PGT. Oh, you mean that the infimum might not be intended? I assume it is. I assume it is. And that's the reason, right, and to solve this problem, I'm not looking for the best approximation. I'm looking for a function which is almost the best approximation. I want this to be small. I'm not imposing the condition that I want to set this to 0. Right? But so even if the infimum isn't attained, I can get arbitrarily close to it. Okay? But I could have, it's slightly more complicated if you're not assuming that your class has the best approximation, but it's just a technicality and I want to avoid it, if you don't mind. Okay? Any other questions? Okay? Yes, no, something? Okay. So, how do I handle this problem from the algorithmic point of view? Right? Remember, all the information I have is a sample, is this. I can't do empirical minimization of this, right? The obvious naive approach would say, try to minimize this because that's what you're shooting for. You're trying to make this close to 0, try to find the minimizer of this. It can't work because I don't know these. I don't know the values of PG at X. Okay, so what I'm going to do is this is just one possible learning algorithm. I'm going to use, this is the only algorithm I'm going to analyze throughout this course. Okay, and it's not the only one. There may be other possible ways of solving this problem. So what I'm going to do is define a learning rule. A learning rule is simply a function which maps for any sample a function in G. Okay, so you take a sample and you get a function in G. Now the question is how to choose the function, right? So the learning rule I'm going to analyze is the following. Given xi, t at xi, I between 1 and n, let's call it L of Sn, right? This is the sample Sn. Let L of Sn be any function in G for which one over n sum I from 1 to n G at xi minus t at xi squared is less or equal than the infimum of G in G of 1 over n sum, let's call it Sn Okay, almost formal. The thing that's written here is a function, the minimal value of the empirical distances between any function G in your class and your target. Right? So when you just look at the sample and you measure distances on the sample, right, this thing is just the empirical minimizer. Okay? And because you're taking the best in your class. So what you're shooting for is a function which isn't the minimizer, but almost the minimizer. Right? Now, you can do that, right, and find the actual minimizer, but from the computational point of view, it's usually much more difficult. And I don't need that. So I'm relaxing the conditions a bit. I fix an epsilon, which is, in some sense, the level of accuracy I'm shooting for, and I'm allowing functions which may not be the optimal, but they're close enough to being optimal. Okay? So that's what I have. Okay? Now, I want to show you at the first step that this means same condition is also true for the loss associated with the class, with this function, right? Here we did something, you see, I can't compute an empirical minimizer straight off with respect to this because I don't know this function, right? So I'm going to do it with respect to this, and now I'm going to show you that it's good enough because it will be an almost minimizer with respect to this. Okay? And the reason for that is, what's the difference between what's written here and what's written here? In both sides, you have exactly the same term you have to add. The difference is, this is just this part without this part. Okay? But this part appears on both sides. Right? So it doesn't matter which function you take. It doesn't depend on the actual minimizer. It's true for every function you take in your class. Okay? So I can just write, writing this is exactly the same as writing 1 over n sum I equal 1 to n LSN xi minus t of xi squared minus this term 1 over n sum t at xi minus tgt at xi squared, less or equal than this term, right? Because you see, here I'm taking the infimum over all elements of the class, but this element doesn't depend on the particular g. It's a fixed term, which is true for every g in your class. So this is essentially the same as demanding that this is less or equal than the infimum of g and g, 1 over n sum g at xi minus t at xi squared minus exactly the same thing, it's epsilon. Okay? So this straightforward computation shows that minimizing this is essentially the same as minimizing this. Right? So from the algorithmic point of view, what the practitioner will do is you take a function, so you take your sample, you take your function class, you find this. Okay? That's the function you produce. It will turn out that this function is also a good empirical minimizer of this. Okay? So, what's the problem now? You found a function which it's, okay, let's write it for a second. So just another small piece of notation. I don't want to write L of Sn all the way through. So I'm just going to call a function which is an almost empirical minimizer. I'm going to call it G star. Okay? So what we have, given a sample, Sn, which is equal to xi t of xi, we found, assume, G star, and G star has the following property that, let's write it like this, 1 over n sum I equals 1 to n L G star. This means the loss when you take G star instead of G, right? So when I say this, I say, look at this, but instead of G, write G star. Okay? Alright, L of G star is less or equal than the infimum of G and G of 1 over n sum equals 1 to n L of G at xi plus epsilon. Right? That's what I have. What is this? What can I absolutely say about this thing? Right? Let's look at it. Right? This is your loss class. What can I absolutely certainly say about this infimum, about its sign? Okay? What kind of candidate can I select for G here? I can take G to be PGT. It's one of the class members, right? So if I take G to be PGT, what I have here is 0. So what I have here is 0, right? So the infimum must be smaller than 0 because I found one candidate which gives me 0. So this means this is less or equal than epsilon. Okay? So using this algorithmic thing, like finding an empirical minimizer, I was able to construct a function which has a loss, an empirical loss, smaller than epsilon. What I would like to show is that this means that the true loss of the function is smaller than epsilon. Remember, what I want to estimate is the expectation of G star minus T squared minus the expectation of T minus PGT squared. What I want to show is that this is smaller than, say, epsilon. Okay? So the question is, if I know this, does it mean necessarily that this is true? Let's have 2 epsilon here. Okay? Doesn't really matter. Okay? So that's the question I want to address. And I want, yes?
What's small L sub G?
This.
Yeah.
This is just, in general, L sub G is simply G minus T squared minus T minus PGT squared. This function, right? It's the loss function associated with the original function G. So L of G star, right, is this when you have G star over here. Okay? So this is the problem I have, right? I have a function which has an empirical mean smaller than epsilon, and I want to show whether its actual mean is smaller than 2 epsilon. Okay? That's the only question I want to address. Okay? Now forget everything I said so far. Okay? Forget the fact that we started with a loss class and a given class of functions and a target function and all that stuff. The question is a purely theoretical question. You have a class of functions, let's call it f, right? You have a function in that class which has a small empirical expectation that this is small. Doesn't necessarily mean that it has a small actual expectation. Okay? So the question we really want to address, and it's completely independent of all the structure I've described so far, all the loss classes, and that is the following. Okay? So let f be a class of functions you want to see whether, and let Sn be a sample. Okay? Now, assume that one over n sum I equals 1 to n of f at xi is less than epsilon. Does it mean that the expectation with respect to mu of f is less than 2 epsilon? Okay? After you forget everything I told you, this is what it boils down to. This is the question you want to answer. Okay? Now, now when we look at this particular question, it's clear that the answer has to be no. right? It's just inconceivable to assume that for every sample you take, the fact that you have that this is small means that this must be small. Because you can take, if you're not restricting anything, you can take points which do not reflect at all the structure of your function and the measure. Remember, when you do that, when you take this, right, let's write it in a form you might like better, integral of f d mu, right? So let's assume that this is omega, and I have a measure over here. So this is I have a measure mu over here. Now assume, just for the sake of argument, that the measure only lives in this part of the world. So in some sense, if you had a density, the density here would be 0, right? Now you take a sample from this part of the world, right? I haven't restricted anything, so you can take a sample from this part of the world. The fact that you have the value here is small is completely meaningless because it doesn't come into account when you compute the integral. The measure doesn't know that something is happening over here, right? So this claim, as it stands, can't be true. You have to introduce, so you have to use the fact that you're sampling according to the probability measure, and some probabilistic argument must come into the game, right? Okay. Where is that one? Over here. So this can't be the right question. How do I make it right? I make it right, let f be a class of functions unless s and does it mean that this holds with high probability? Okay? Does it mean that it holds with high probability? Now, when I write it like that, it's also an ambiguous statement because I haven't told you with respect to what probability I want this to be high. Right? You may say, okay, I'm sampling according to one probability measure, but I want this with respect to another probability measure. And for the same argument I used before, the answer is it's impossible. Right? Because of the two probability measures, the one you sample according to it and the one you're computing this aren't the same, you can always construct lousy examples. Okay? So this holds with high probability mu. Okay? So, is this true? What do you think? I have to have an opinion. I don't have an opinion? Okay, let's start with one example. Okay, I want to show you, well, what could this problem depend on? It can depend on two things, right? It could depend on the specific probability measure I have, right? And it could depend on the class. Okay, now I can't do anything with respect to the probability measure because that's given. I can't control the way I'm sampling. Somebody gave me that probability measure. So the question is, what properties of the class can this be true for? I mean, what's important? And what I'm going to try to convince you is that the most important thing is the size of the class. Now, the question will be, what is the right notion of size? Okay? Now, first of all, I want to show you that this kind of statement can't be true if you're not assuming anything on a class. Okay? So I'm going to give you one particular example, okay, for a class for which this isn't true. Okay? So, here it is. We'll do that and then we'll have a break. Okay, so assume your class consists of the following. It's simply the set of all the continuous functions on the interval 0, 1, bounded by 1. Okay? So f is all continuous functions on 0, 1, which are bounded by 1. Okay? Now, not exactly that, right? That's not F. Let's call this, I call this set B. And F is all the functions of the form G minus G0, where, let's have absolute value here, where G0, if G is in B, and G0 is the following function. So this is G0. So what I want to do is to measure how far away I am from G0. Okay?
Is B not bounded below?
When I say bounded by 1, meaning that the absolute value of every function is bounded. So the functions are between 1 and minus 1. Okay? That's what I mean bounded by 1. Okay? Now, assume that a statement like this will be true. Okay? Then for every function I produce which has a small empirical mean, it will necessarily have a small actual mean. Okay? Now this means that if I can find two functions which approximate G0, they have to be close. Right? Because the difference is that if you look at G1 minus G0 and G2 minus G0, both their expectations are small, so they can't be too far apart. Okay? Just think of it from the philosophical point of view. What I'm actually doing is constructing an approximation of G0. If two functions approximate the same function, they have to be close. Now what I'm going to do is to construct two functions which empirically approximate G0 perfectly, but are very far apart. And both of them will be in this class. Okay? So here's one function. Is there a color here? 1, 2, great. Okay, so now I have a sample. Okay? Here's the sample I have. The points of the sample are just here and here. Okay? So the sample, let's say this and this. Okay? The way I can assure that every sample generates points only here and here is simply to assume that the measure is supported here, meaning that you have no chance of sampling points here. But that's just a technical thing. Okay, now I'm going to construct two functions which are exactly G0 on the sample, meaning that this for them will be 0. Okay? So here's one function. The one function would be 1 almost wherever I want it, except where I have to make it 0. So the function here is 1, 1. Now I have to go down to 0, but I can do it very, very close to this point. Very close. Okay, so this is one function. The other function is 0, except in places I have to make it 1. So I have to make it 1 here. And everywhere else it's 0. Both these functions are perfect approximations. For both these functions, this will be 0. They completely coincide with the unknown function at the sample, so this is 0 when you compute the empirical average. Now, assuming that this were true, they have to be close together, but they're not. This function is 1 almost everywhere, except a very small, and this one function is 0 almost everywhere. Right? So the difference, they're very far apart. So this statement can't be true unless you restrict your class of functions. And for example, the class of continuous functions bounded by 1 is simply too large. It doesn't tell you what conditions you actually need, but this tells you that this is way too big. Okay, this is a good time to have a break, and after that we'll see what I showed you what you can't do. I'll show you what you can do. Okay. What's the normal, Alex? What's the normal break time?
Well, 5 to 10 minutes, as much as you wish.